In this video, we're going to look at the features of a polynomial function. We are given in this problem that we're working with f of x, and they've already graphed f of x for us, so we're just going to analyze the graph and use the function as well to answer a few questions. The first question asks, are any intervals of increase? And looking at the graph, I notice that there is an interval of increase right here. And there's a second interval of increase right here where the graph is increasing as we go from left to right. Now I notice on the left side of the graph that it actually keeps going on forever to the left. So in this case, I know that it's going to keep going to the left all the way until negative infinity. When we're writing interval notation, we always use the x-coordinates. So for this first interval of increase, I know that it goes all the way over to negative infinity because it keeps going to the left, and it's going to go all the way up to -1. So this point right here where it stops increasing. And typically when we're working with intervals of increase and decrease, we use the parentheses as our interval notation instead of the square bracket because really it's not increasing or decreasing right at the point -1, 0. Now for the second interval where it's increasing from an x-coordinate of 0 all the way up to an x-coordinate where it stops right here at 2.11. The next question asks for the intervals of decrease. So where is it decreasing from left to right? And I notice the first place it decreases is right here, and the second one is over here. For the first interval of decrease, it's decreasing from an x-coordinate of -1 all the way until it reaches an x-coordinate of -0.35. So those are going to be my endpoints for the interval. So -1 all the way up to 0.35. And then it's also going to start decreasing again at 2.11, and it's going to continue decreasing for x values all the way to positive infinity. So we go from 2.11 all the way up to positive infinity. The next question asks for the local maximum and local minimum. The maximum on the graph, or local maximum, is where it reaches a point and then goes back down. Here's another maximum where it's going up and then it goes back down. So it's going up, reaches the local maximum, and then goes down. We call it a local maximum because it's only part of the graph instead of the absolute maximum for a function. So this question is just asking for the local, so we have two local maximums, and the values for the maximum are at y equals 0 and y equals 3.63. Now when you're identifying maximum and minimum values, it's common to just use the y values, but you can also use an ordered pair. The local minimum is similar, except that's where the graph bottoms out and then turns back around. So you can see right here it's going to bottom out and turn back around. So that's that's our minimum, or local minimum right there. Now it's not an absolute minimum because we can see that the graph actually continues to go down on both sides. So it's not the absolute minimum, it's just a local minimum, and that is at the y value of -0.1. And I get that from the ordered pair that's listed at the minimum right here. Next, we have the real and imaginary zeros. Now this is going to require us to do a little bit of work. So we're going to use the function that we were given up at the top, which is f of x equals -0.2x times x plus 1 squared times x minus 3. And they're asking for the zeros, which means where the graph crosses the y-axis right here. Now, it's not just the x-intercepts because they also ask us for imaginary zeros. So what we're looking for are what are called the roots, or where the function is equal to 0. So I'm going to start by changing our f of x to 0 and then rewrite the right-hand side. And next I'm going to use the zero product property, which says if I'm multiplying things together and I get 0, at least one of them has to equal 0. So I'm going to set each of the three pieces equal to 0 separately. So I have 0 equals negative 0.2x, 0 equals x plus 1 squared, and 0 equals x minus 3. And then I just need to solve each of those equations separately. The first one's going to be fairly easy to solve. We just divide both sides of the equation by negative 0.2. And that will give us that x is equal to 0, because 0 divided by any non-zero number is just equal to 0. For the next problem, we have this squared that we need to get rid of. In order to get rid of the squared, we need to square root. So I'm going to square root both sides of the equation. And when I square root, I always want to consider that there's a possibility of a plus or minus. Now in this case, the square root of 0 is just 0, so we really don't need to worry about the plus or minus. So now I have 0 equals x plus 1, because the square root and the squared undo each other. So the last step for this one is just to subtract 1. And I have that x equals negative 1. And the last one, here we just have one step, add 3 to both sides, and I get, in this case, I have 3 zeros, and they all happen to be real zeros, which means we didn't have to take the square root of a negative number anywhere in order to solve for x. So our real zeros, I'm just going to list them right up here. X equals 0, negative 1, and 3. And if we take a look at the graph, you can see that it does in fact intersect the graph, or the x-axis right here at negative 1, at 0, and then over here at 3. So we could have looked at the graph for that, but we also want to be careful because the imaginary zeros will not show up on the graph. The last thing they asked us to do is to look at the end behavior, and the end behavior is just what's happening at the end of the graph. In this case, the graph is going down on both ends. So to the right it's going down, and to the left it's going down. So we can write that just using words and say that it's going down to the left and down to the right. There is another way to write this, and that is using our f of x and x, and using arrows to indicate where our x values are going. So one way we can say it is as x approaches negative infinity, so in other words, as we're going to the left, what's happening to our f of x values or y values? In this case, they're going down, which means that the y values are also approaching negative infinity. For the right-hand end, we can say as x approaches positive infinity, in other words, as we're going to the right out here on our graph, I can see that the y values are going to negative infinity again. So then we can say f of x approaches negative infinity. So that's another way to write end behavior if you don't want to write it using words. So those are the features of a polynomial function. Hope that helped. Have a great day.